Before I get into the actual examples of using substitution to solve a system of linear equations, I want to go over the basic logical concept of what it is that we're doing in the first place so we can see why is it legal? Why are we allowed to do this in the first place? And I want to do this by not using numbers and letters, but instead using some visual aids. So these are very crude drawings, but what we got here is we have some balance scales. So the first balance scale that we look at says one square weighs the same or balances out four triangles. And the second one says two squares balances out with three circles. So I want to take a look at this for a second and say, let's look at a third balance scale. And suppose I want to balance out three circles with it. Well, we know that two squares would balance it out, but if instead of using squares, I wanted to use triangles, how many triangles would I need? Well, if we look back at the first balance scale, one square can be balanced out with four triangles. So I could erase one of those squares and balance it out with four triangles. And then similarly, I can erase the other square and use four triangles for him as well. This is the idea that we're going to actually use for substitution. That we're going to say, if I know that one square is the same as four triangles, then anywhere I see a square, I can replace it with the four triangles. That's perfectly fine. They're going to stay balanced. And that's what's going to be going on algebraically with the substitution method. As we look at this first example, our one square to four triangles matches up with our y equaling 5x. The fact that y equals 5x says anywhere that there's a y, I can replace it with 5x because they're literally the exact same thing. They're equal. So we're going to use this equation and substitute it into the first. So that everywhere that there's a y, right there, we're going to replace that y with a 5x. And hopefully you can see the beauty of that then. We went from having these two equations that both had two variables in them, and we don't know how to solve an equation that has two variables in it. But then we replaced all the y's in one of them with x's, so that that equation now only has x's in it. If we have an equation that only has x's in it, then we know how to solve that. So we can solve that by combining like terms and then dividing by 6. And saying, hey, the x value is negative 7. And if we know that the x value is negative 7, then we could actually plug that back into one of the equations and find the y value. So if I replace the x with negative 7, I find that the y value must be 35, and that gives me an ordered pair. Now, does it matter that I plugged it into the second equation? No, because a system of equations is two lines. If it works in this equation, it better work in this equation too, because the point I'm trying to find is their intersection. It's the point that's on both lines. So it doesn't really matter whether you plug the negative 7 into the first or the second. Now with that said, it's going to be easier to plug it into your substitution equation, the one that was already solved for y, because I didn't have to do any algebra. I just had to do arithmetic. It's pretty easy. Let's step it up in difficulty a little bit. So in this one here, we do have a y equals already. That's what we want to look for. When using substitution, you want to look and say, do I already have one of the equations solved for either x or for y? It doesn't matter which one. If not, can I easily get there? So in this case, we do already have it solved for y. So in this case, y is the exact same thing as 3x plus 16, which means anywhere that we see a y in the equation, we can replace it with a 3x plus 16. Now we always want to plug it into the other equation, not back into itself. That wouldn't make sense. So if we rewrite that first equation, but just replace any y with 3x plus 16, then if you look at what we have now, we have an equation that only has x's in it. And so that's pretty cool then. We can solve it. We can distribute the 5 to get negative 15x minus 80 is negative 24. We can combine like terms. Now if we add 80 to the other side, we'll have a positive 80 minus 24 is 56. And so negative 14x equals that. And then if we divide by negative 14, we get x equals negative 4. And once we get x equals negative 4, we can plug that back in to either of the equations. But as I said, the substitution equation will typically be easier. So we get y equals 3 times the x value, which is negative 4, plus 16. So that's negative 12 plus 16, or 4. Just to be clear, that's positive 4. My equals just got close to each other. And so this gives us an ordered pair of negative 4, positive 4. Remember, with your ordered pairs, it should always be x comma y, that your x comes first, even if you happen to have solved for the y first. It's always an ordered pair, x comma y. Now here's an interesting situation in which they're both solved for y. We have y equals 3x plus 5 and y equals 4x plus 6. Now in this case here, we can use either one as the substitution. If we use this top one as the substitution, then we're saying anywhere that we see a y, we can replace it with a 3x plus 5. So we can rewrite the second equation, just replace any y that we see with 3x plus 5. And now we can solve for x by subtracting 3x from each side, which gets us 5 equals x plus 6. Then subtract 6 from each side, and that gets us x equals negative 1. We can now plug this into either one of the equations, doesn't matter. But y equals 3 times negative 1 plus 5. And so y must be 2. And so our ordered pair is negative 1, 2. How about this one? Holy cow! This looks disgusting. But we don't have to deal with fractions. You can look at this and say, wow, fractions suck. Let's get rid of the fractions. We can legally do that by multiplying both sides of the equation by the LCD, by the least common denominator. So between 7 and 3, the least common denominator is 21. We're going to multiply both sides of the equation by 21. For the second equation, we could multiply both sides of the equation by 36, because that's the LCD there. That's going to get us, let me go ahead and write it off to the side. It's not normally good math, but it's going to help save some room. We're going to multiply 21 by each term in that equation. For the second one, we're going to multiply by 36 in each term. And then you can see the beauty of why we chose to do that. 21 sevenths is 3. 21 thirds is 7. 36 fourths is 9. And 36 ninths is 4. Now we're still going to run into a little bit of a problem here. In order to use the substitution method, we need to get one of these variables by itself. And that's going to introduce some fractions into the problem that we're going to have to deal with. And that's really the motivation for the next algebraic method. We're going to look at another method in a little bit where we can solve this without having to deal with fractions at all. But let's go through this substitution method because I did want to show you one where it's not already solved for in and of itself. So I would solve for the x in the first equation because the coefficient is smallest. But in doing so, notice I put an asterisk next to it. I want to remember that that's the one that I'm solving for a variable from. So that when I plug it back in, I plug into the other one. That's really, really important. So as I try to solve for the x, I would subtract the 7y to the other side, and then divide by 3, giving me negative 7/3 y plus 7. So we have solved for x, meaning anywhere that we see an x, we can replace it with negative 7/3 y plus 7. So we're going to run it back into that guy there, where we have 9 times, instead of x, we have negative 7/3 y plus 7 minus 4y equals 36. Obviously, this is looking ugly, but let's keep going. We distribute the 9 across that parenthesis to get negative. Well, let's see, this one's actually not going to be that bad because 9 divided by 3 is 3. And then 3 times 7 is 21. So we actually don't have fractions anymore. So that's not too bad. 9 times 7 is 63. Okay. We're going to combine like terms to get negative 25y plus 63 equals 36. Now we're going to subtract 63 from both sides. 36, oops, if I can type this in my calculator right, 36 minus 63 is going to get us negative 27. Which means when I divide by negative 25, I get y equals 27/25. Ugh. We could continue this problem out now and try to solve for the x by plugging back in to this equation where we had x equals negative 7/3 times our value of y, which is 27/25 plus 7. Now, we're getting kind of ugly here, so I would use my calculator if I were you. So I would bring this calculator up, and I would say I have negative 7/3 times 27/25 plus 7. And we get 112/25. This is not a fun answer at all. We get this ordered pair 112/25 over 27/25, but you cannot tell me that I'm only giving you simple examples then and making you do worse in the homework. So this is definitely an ugly answer, but part of the reason I did want to go over this was to point out that this is not the ideal problem for the substitution method. In the next video, we're going to look at the addition method, which is going to make a problem like this much easier. We get the same answer. Of course, the answer is going to be the same, but the addition method would make it so that we don't have to deal with fractions throughout any of it, and plugging it back in is not going to be so ugly. So we're going to get there.